Start our next session, which would be concentrated on uh, X-ray free electron laser research. And I would like to invite next speaker, which would speak about Attosecond X-ray free electron lasers, and it will be Professor Vitaliy Goryashko from double affiliation from Sakla, Japan, free electron laser, and from Uppsala University.
Yes. Yes. Hello, everyone, and konnichiwa from Japan. All right, let me share the slides. Mhm. So do you see full screen?
Yes, of course. Perfect.
Let's see if laser pointer works well. And also the laser pointer works, right? Is it all right?
Yes, yes.
Yep. Good. So let us set the stage. We will be talking today about attosecond physics. So let us understand what are the scales that we're interested in. Let's consider a simple hydrogen atom in the ground state. Just one electron orbiting around the proton. The characteristic energy scale is 10 atom volts, and the spatial scale is 1 angstrom. It takes 150 attoseconds for the electron to make one turn around the nucleus in the quasi-classical approximation. The Heisenberg uncertainty limits accessible pulse durations for a given energy. So for energy of 0.33 electron volts, the shortest possible duration is 0.3. For an energy of 1 electron volt, the shortest possible duration is 0.33 femtoseconds. So let's see where we can find such time scales. Not in nanostructures, because the characteristic energy interaction is on the sub-electron volt. In molecules, valence electrons usually have energies few of tens of electron volts, still not enough for attosecond physics. But if we look at the core electrons in atoms, the interaction energy is typically much larger than 10 electron volts. And then the dynamics of core electrons happens on the attosecond time scale. That's where we need this resolution and this precision. Let's see what kind of science drivers motivate this development of attosecond physics. There are different processes which happens on the femtosecond or even sub-femtosecond time scale. This plot shows the time scale in femtoseconds, and the horizontal scale shows the energy. That is the characteristic interaction energy. In the low energy region of this plot, we find such processes as charge migration, charge screening, photoionization dynamics. All these processes are very important for understanding how the molecule functions. I will give an example on the next slide. If we are talking about high photon energies, then the interest is in Auger decay, Coulomb explosion, and different kind of coherences. Let's take a look at the charge migration. So what is that? Imagine we have a molecule and we ionize one side of the molecule and remove one electron. That gives rise to a hole. What happens with the hole? How does it move? And how does it migrate within the molecule? So this question is important for understanding the energy transfer on the molecular level. Here on the right, you can see an example. This is an experimental study by Ferenc Krauss, who got the Nobel Prize in 2023. In the experimental study, they used a molecule of iodoacetylene, and the iodine side of the molecule was ionized. So it's quickly ionized. One electron is removed, and we see that after half a second, and so this this shaded area schematically shows the hole which appeared after the ionization. After half a second later, the hole delocalized over the molecule, and we see that 1 second later, the hole is localized on the acetylene side. 1 second later, the hole is moved back to the iodine side. So the whole process takes around 2 femtoseconds. So this study was done actually using an HEG source. So we see that indeed the whole dynamics happens on the femtosecond time scale, and in order to resolve this motion, we need attosecond precision. Let's see what kind of sources are available to study attosecond dynamics. The plot on the left shows accessible pulse progress in the generation of shortest possible pulses as a function of time. So the first lasers, they were continuous. But shortly after the discovery of the laser, the technique of mode clocking was developed. So this technique of mode clocking made possible generation shorter pulses and down to the regime of some femtoseconds. So the picosecond barrier was broken in the 70s, and the generation of pulses as short as 5 femtoseconds were demonstrated around the 80s. However, for around 20 years, the progress stayed on a plateau. So there was really no future progress in shortening the pulse duration. However, during this period, two important techniques were developed: short pulse amplification in lasers and high harmonic generation gases. So the technique of short pulse amplification received the Nobel Prize, if I remember correctly, in 2018 or maybe 19. And the technique of high harmonic generation gas received the Nobel Prize in 2023. So these are two very important discoveries in physics which made possible accessing the attosecond time scale. At the same time, we see that in recent years, the progress in the second pulse generation started to slow down. However, using advanced concepts based on duet radiation, it's possible to further reduce the pulse duration, and there are ideas how to generate pulses as short as few attoseconds, or even on the sub-attosecond pulse region. Here is another visualization of the progress in the short pulse generation. So on the left, you see the pulse energy as a function of the pulse duration. Most of the results with ultra-short pulses were demonstrated using HEG sources. So that is the current frontier of science. First FELs, first fractal lasers, made possible generation of femtosecond pulses with very high energies on the millijoule scale. The first generation of attosecond pulses with FELs was demonstrated at LCLS around 2017, and they reached pulse durations as short as around 250 attoseconds. At the same time, using new ideas based on duet radiation, it's possible to reach the terra incognita of ultra-fast world and generate pulses as short as 10 attoseconds or even shorter. An X-ray field is a unique instrument. Not many X-ray fields exist around the world. One example of the first field is Flash in Germany, in Hamburg. That was a 1 GeV machine, which at that time was 300 meters long, and now it's a small field, 300 meters. Nowadays, it's nothing compared to modern field monsters. And that was in VUV X-ray field. In 2009, LCLS started its operation, shortly after followed by the operation of Sakurai field in Japan. So LCLS that demonstrated for the first time generation of femtosecond X-ray pulses. But the machine was huge at the time, 1.6 kilometers. At Sakura, they used several innovative ideas and made the laser just 600 meters short. After that, almost like a decade later, a bunch of other EFLs came to operation. Polyfield in Korea, then Swiss EFL in Switzerland, and the European EFL. So my colleague, Svetozar, he will talk in detail about the European EFL and how they generate attosecond pulses there. But that is a monster machine, 3.6 kilometers long, and accelerates the beam up to 20 GeV. There are also ideas how to make more compact EFLs, like the idea proposed a few years by the European Consortium of Compact Light, that would be just 400 meters with more affordable price. Meanwhile, in China, they're building another monster, the Shine facility, which will be 3 kilometers long based on superconducting linac. And in the States, now they're upgrading LCLS2. All right, there are really many ideas have been put forward how to generate attosecond pulses. So here you see lots of ideas. I will not describe in detail these ideas, but I will just quickly go through. At least you will see what happens in the world of attosecond X-ray fields. Because these methods, they are very different and serve different user needs. And sometimes it doesn't really make sense to directly compare different methods, because it's like a racing car versus a truck. They serve different functions, different purposes. All methods of generating ultra-short pulses and fields, one can divide into two broad areas. One bunch of methods is based on the field process itself, and another group of methods is based on preparing a very short electron bunch. So the first group makes use of single SASE or single SASE spike field radiation, or pulse self-compression in the super irradiant regime, tapered field, mode locking, and other advanced concepts. Or the second group of methods, it relies on making a very short electron bunch, such that when it goes through an undulator, it emits coherent radiation, just one very short SASE spike. I'm afraid that most of you are not really familiar with the field physics, but nevertheless, let me just give you a quick outline what happens and what kind of developments has been demonstrated and what is possible to achieve nowadays. First of all, I need to mention that in the field, the pulse is not coherent. So the radiation pulse, it's the power, it's a function of time. The radiation pulse consists of a series of shorter radiation pulses. That is because any field starts from short noise. It's not really a laser. It's not really coherent in terms of temporal properties. If we can make the electron bunch very short, then it will emit just only one radiation pulse, and this radiation pulse called SASE spike. So for soft X-ray fields, one radiation spike or one radiation pulse is typically between 0.5 and 1.5 femtoseconds. For hot X-rays, this one radiation spike is shorter, typically 0.15 to 0.4 femtoseconds. So the challenge is to prepare a short electron bunch. All right, how we can do that? The simplest idea is that an electron bunch from an accelerator forced to travel a curvilinear path, and on this path, one inserts a screen with a small wedge-like opening. So that is the method called slotted foil. So most of the electron bunch is destroyed, and only one short part of the electron bunch is good and able to produce radiation in an undulator. So in this way, it was for the first time demonstrated LCLS. They showed, so they produced an electron bunch as short as 1 femtosecond and demonstrated lasing at 5.6 keV. And in this way, 65% of shots, 65% of pulses were just single spike. with an average energy of 5 microjoules. And you see, with the duration as short as 400 attoseconds. Later, again at SLAC, they demonstrated the method of nonlinear compression, which allows producing very short atom bunches just by squeezing them in the longitudinal phase space. In this way, they demonstrated lasing at 5, or let's say 5 and 9 keV, and with the pulse duration as short as 230 attoseconds. So it's really the attosecond time regime. That is more advanced concept. It's based on the fact that during the nonlinear process, the pulse duration naturally reduces. So the radiation pulse forms some sort of soliton, and this soliton squeezes as the pulse is amplified during the field. So that is a visualization. That is a simulation, which was also tested experimentally. So this white line shows the width of the radiation pulse. And we see that after some point, the radiation pulse started to reduce longitudinally. This effect is difficult to use, but it's demonstrated, and actually it works. Maybe in the future it will be implemented somewhere. So that is an advanced scheme from Takashi Tanaka from Sakurai field, in which he proposed to use to select one part of the atom bunch, modulate the certain bunch using external laser to produce short spikes of the electron current, and when this electron current goes through an undulator, it generates a series of radiation pulses, and then the pulse length decreases down to the level of 50 attoseconds in simulations and reaches a very high peak power. But this method actually is quite complicated because it requires a very precise control between this radiation, between these micro bunches of electrons and radiation pulses. So therefore, there was a number of techniques which are much simpler and use different variations of the slotted foil. So what I already briefly mentioned, this is in this way the quality. So some parts of the electron bunch are removed, and only short pieces or short microbunches allowed to generate in an undulator. So what we see here, that is the distribution of that's the electron distribution, and only these short regions are allowed to produce radiation in undulator. And in this way, they demonstrated, I think that was already an experimental study, they demonstrated generation of 200 attosecond pulses with an energy up to 200 microjoules. The next development was also at the Swiss FEL 2015. They proposed to use different parts of the electron bunch. So what they proposed, they, instead of sending the electron beam directly through the undulator, they gave a kick to the electron beam, so it starts to oscillate transversely as it propagates through the undulator. So only a small group of electrons actually is lasing inside the undulator, because the rest are coming in the wrong phase. So in this way, they demonstrated lasing of 2 femtosecond pulses at an energy 670 eV. And around 10% of spikes were, and 10% of pulses were single spike.